Let's begin now. Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bohr Center for Cyber Physical Systems, IIC. Today's talk is by Dr. Geethu Joseph, and she will be speaking on sparsity-constrained linear dynamical systems. Dr. Geethu Joseph received the BTech degree in Electronics and Communication Engineering from the National Institute of Technology, Calicut in 2011, and the ME degree in Signal Processing and the PhD degree in Electrical Communication Engineering from the Indian Institute of Science, Bangalore in 2014 and 2019 respectively. She was a postdoctoral fellow with the Department of Electrical Engineering and Computer Science, Syracuse University, New York, from 2019 to 2021. She is currently an assistant professor in the Circuits and Systems Group at the Delft University of Technology, Netherlands. Her research interests include statistical signal processing, network control, and machine learning. She holds 20 plus peer-reviewed publications in the fields of signal processing, communications, and control theory. Dr. Joseph was awarded the Professor ISN Murthy Medal in 2014 for being the best ME student in the ECE department, IISc, the 2020 SPCOM Best Doctoral Dissertation Award, and the Sheshagiri Kaigini Medal for the best PhD thesis of the ECE department at IISc for the year 2019 to 2020. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Joseph directly or type them in the chat box and we will moderate it with. Over to you, Dr. Joseph.
Thank you, and hello everyone. I'm glad to be at least virtually at IISc. Today's talk is about sparsity constraints that arise in linear dynamical systems and how these constraints will affect the control properties of such systems. This is a topic which I picked up during my PhD days at IISc with Chandra. And later I continue to work on this topic with different master's students at IISc and other researchers from different other universities as well. So I'm very glad to present our results on this particular topic. So why do we need sparsity constraints? Consider large-scale or geographically distributed networks. It could be social networks which connects people like Facebook or Twitter, or it could be power grids, traffic networks, biological networks, etc. So these networks could be like very large scale, or it could be located at different places. It could be geographically distributed. So controlling such systems is in general challenging. So what happens is that these networks these systems will have different degrees of freedom. You could tune it at different places, and it may not be feasible to control all of them at the same time. For example, consider a social network which consists of a lot of people, and these people will talk to each other, they influence each other, etc. And if you want to place an idea, or if you want to influence this network, if you want, for example, if you're launching a product and you want everybody to have a good opinion about your product, you cannot go and influence each and every person in the network. So instead, what will you do? You will just go there, you just try to influence the most trusted people and let them influence others. So an optimal strategy to control such large networks involve a couple of conditions. First one, we need a simple structure. You don't want a very complex control strategy. And we need a sufficient performance level. So the performance level definitely depends upon the particular application. And we also want low communication and computational complexity. So if you have a network control system, your actuator could be at one point, your control system, so you'll be giving signals from another point. So you need a low communication burden. You need to work with low band wireless links. And you also obviously want to keep the computational complexity low. So for large scale systems, people typically tend to move from a fully centralized version, because it's almost impossible, to something like a decentralized version. But what can we do instead of these two? So that's what we explore. And one option is sparse control. So what exactly is sparse control? We'll see that in a minute. So sparse control, if you're looking at sparse control, it's all about a control vector with a lot of zeros. So your control vector at any time will be a big long vector, and most of the entries will be zeros, which immediately implies that we use only a few of the actuators among all the available ones. So it'd be large network with a lot of actuators, but we only try to tune a few of them at a time. And the good part is if you have a sparse control, it also admits compact representations because there is one area in signal processing called compress sensing, which talks about how to compress sparse signals, how to recover them, etc. So such sparse control will be simple because you have to tune only few actuators at a time, and it is communication efficient because it always admits compact representations. So it works very well with bandwidth constrained systems. And also you have a lot of zeros. So naturally your computational complexity is also expected to be low. So sparse control is a nice alternative that we can try. In this talk, what we're looking is sparse control in discrete time linear dynamical systems. So we consider linear dynamical systems that evolve with time. And what happens when we try to control such systems using sparse control. So the talk will have three parts. The first, we look at the feasibility of sparse control. So you're not using all the actuators that are available to us. So what do we lose because of that? Definitely we lose something. So when does it work and when does it doesn't work? So that's what we look at the first part. And also if we know that the system admits sparse control or sparse control works, then how do we design sparse control? That's the next part. And finally, we look at a case study based on social network opinion manipulation. Okay, so this is the mathematical model that we'll be working with. We consider linear dynamical system, which means we can use state space model, which consists of two equations, state evolution and observation model. State evolution says that at any time k, the system state xk has is determined by two components. The first one is the influence from the state of the previous time given by a times xk minus 1, and a is called the transition matrix. Plus we have another term which comes because of the input. So b is our input matrix and uk is the input vector. Then we have observations yk, which is equal to c times xk plus wk, where c is the observation matrix or the output matrix. So you don't get to see xk all the time. You see c times xk, but a noisy version of that. So wk is a noise in the observations. So with this state space model, the question that we ask is, suppose we constrain the inputs, that is we constrain UKs. Let's say UKs are, the L0 norm of UK is less than capital L, where L0 norm just counts the number of non-zero entries in UK. And L is the dimension of UK. So the number of non-zero entries in UK is very small compared to its dimension, and it applies for all k equal to 1, 2, 3 all the way. So if that is the case, then how does the control property of the system changes? So we can consider two cases. The first case is the time invariant support. That is, you fix a support meaning the indices of the non-zero entries of UK, and then you continue with that. In other words, we choose a set of actuators and we always tune them only. We don't really control the other actuators. So that is one option. Another option is a time varying support, which means at every time instant, we choose different set of actuators, but at every time we choose a small set of actuators, not everybody. So that is a time varying support. So when I say support, support is a set of non-zero indices of this sparse control UK. So time invariant means the actuators that you control is fixed, and time varying means we can possibly control different actuators at different time, but at a given time instant, you can only control a few of them, not everybody. So this is the system model that we're going to work with. So first, let's look at the feasibility of this particular model. So when does it work? And to do that, we look at something called controllability using sparse inputs. What is controllability? Controllability is the ability of a control system to start from any given state and to reach any other given state. So for any initial state X in it, and for any final state X final, should be able to find control inputs that can take you from X init to X final. So in finite time. And let's say you're reaching X final at K time steps, capital K time steps. Then from your state space model, the relation between X init and X final and the control inputs is given by the equation here. So X final minus a to the power of K times B times X init is equal to controllability matrix times the vector with all the inputs. So controllability matrix is a standard notion in control theory. And the question is it possible to solve this system of linear equations for any initial state X init and any final state X final? So for any initial state X init and any final state, should be able to find a capital K, which is finite, and we should be able to find U1, U2 all the way up to UK, which satisfies this particular equation. If that is, if such a solution exists for any initial and any final states, then we say that the system is controllable. And there are two classical tests to check whether the system is controllable or not. So these are the tests without any constraints on the input. So your input can be anything, it need not be sparse. For the general non-sparse setting, we have two tests. The first one is a Kalman test, which says that put a K capital K equal to N and check the rank of the controllability matrix. So the controllability matrix can be obtained by substituting capital K equal to N in the first equation, and the rank of the resulting matrix should be N. In other words, that matrix should be full row rank. And there's an alternate and equivalent test, which is called Popo-Belevich-Heath's test. We call it PPH test for short. This test checks for rank, but this time it's a rank of A minus lambda times identity matrix, horizontally concatenated with B, which is the input matrix. And rank of this particular matrix should be equal to N. So this matrix should be full row rank. And this should be full row rank for any given lambda, any complex number lambda. So this test is called the PPH test. So Kalman test and PPH tests are equivalent. So if one succeeds, the other one also succeeds, and if one fails, the other one also fails. So these are two equivalent notions or equivalent tests to check controllability of unconstrained systems. Now let's see our problem. So in our case, we want to solve this particular set of equations under the constraint that UKs are sparse. So we start with the time invariant case, which means the non-zero entries of all the UKs are the same, or the support of UK is fixed for all values of K. Let's assume that the support of UK is denoted by a set S. So S denotes the actuators that we are going to select. So we have 1, 2, all the way up to capital N actuators. And S denote the subset of actuators that we choose to control. And once we choose S, then all the UKs will have the same support S. So we don't change the set of actuators at every time, but we work with a fixed set of actuators. So if that is the case, then the controllability problem is equivalent to having a K, which is again finite, such that we can solve the given set of equations under the constraint that UKs, U1, U2, all the way up to UK are sparse, and they have the common support, which is denoted by S. Note that if some of the entries of UKs are known to be sparse, then the corresponding columns of B doesn't really affect your equation. So we can replace U1, U2, all the way up to UK with their sub-vectors indexed by S, because everywhere else in S complement UKs are zeros. So we can eliminate the zero entries and we can just keep the non-zero entries. And similarly, we have to get rid of the columns of B. So we only keep the columns of B corresponding to S, and we remove everything else. So we get a simplified equation. So the controllability condition under the time invariant support case is to have a solution to the system of equations where your B is replaced by B sub S, where S is a support. Okay. So this particular condition is equivalent to the unconstrained case, So we can have a simple controllability test here. So what is a controllability test? The resulting system of equations A comma Bs should be controllable. That's the result that we get. So when we have time invariant support, the controllability test is as follows. There should exist a capital K, which is finite, and a support set S. So S is a subset of the set 1, 2, 3, all the way up to N. S denotes the set of actuators that we're going to control. And we don't want to control more than S actuators. So the cardinality of set S should be equal to S. And the rank of the matrix which comes from the PBS test should be full row rank. So the rank of the matrix obtained by horizontally concatenating A minus lambda I and B sub S, which denotes the submatrix of B indexed by the columns indexed by S, and that matrix should be N. But there's a problem here. We have to test this for all possible values of support set S. So if we have N actuators, there are N choose S ways of choosing this as set S. So this problem is known to be NP hard. So this is a tough problem to solve. But what is more interesting is, if you relax this assumption of time invariant support, and if you allow this support to change over time, then we have much more interesting results. We'll see that in a minute. So let's look at the sparse controllability, where the support is vary. So again, the problem remains the same. We want to solve the set of equations under the constraints that U1, U2, all the way up to UKs are sparse. We know that in the earlier case, we want the support to be constant across all the UKs, but here we relax the assumption. We say that U1, U2, etc. can have potentially different supports at different times. So let's assume that support of UK is S sub SK. So we see that the support is indexed by K. So for every time we have a different support. Again, SK comes from the set of actuators, that is the subset of the set 1, 2, 3, all the way up to N. The controllability conditions changes slightly here. So the question is whether there exists a K, which is finite, and a set of support set S1, S2, all the way up to S capital K, such that the span of the resulting controllability matrix is equal to R power N. It's equivalent to say that R power N is equal to a union over all possible supports for SKs, and the union over the corresponding, the span of the corresponding controllability matrix. One thing to notice here is that on the right-hand side, we have a finite union of subspaces. Why is this finite? It's finite because our K is finite, and we have only finitely many options for SK. So SK is basically a support of support which comes which is a subset of the set 1, 2, 3, all the way up to N, and we can choose only S entries from the set. So SK possibly have N choose S possibilities, which is again finite. So what we have on the right-hand side is a finite union of subspaces. And we want the finite union of subspaces is equal to another vector space R power N. And the simple results from linear algebra tells us that if union of subspaces, finite union of subspaces is another subspace, then one of the subspaces in the union should contain everybody else. In other words, we can have a much simpler condition. And what it says is that there exists a K, which is finite, and there exists a sequence of supports S1, S2, all the way up to S capital K, such that each support set has at most small s number of entries, and the rank of the resulting controllability matrix should be N. So what is different here? In the earlier case, when we had time invariant support, we had the same support for all time instants. But now we can have potentially different supports, like we have S1, S2, all the way up to SK. So they could be different. But again, we have the similar issues here. SKs could be, we have N choose S options for SKs, and we have to search over different values of K. So this is also if you directly try to solve this or directly try to check this condition, this Kalman rank type condition, this is going to be combinatorial and very hard to solve. Also, we don't have a PBH type test here. We are using a Kalman type test here. So what is different is in Kalman type test, you have to compute different powers of A. If you recall, in the PPH test, it was A minus lambda I and B. But here we have different powers of A involved, which can also lead to numerical instabilities. And solving this doesn't really give us any insights to what is the minimum sparsity level that will ensure this condition, etc. So we asked the question, can we find a simpler sparse controllability condition, which is very simple and straightforward, which does not involve combinatorial computations? We want to have a polynomial, a controllability test, which can be computed in polynomial time. So in order to do that, we first look at the necessary conditions. So we make a few observations here. First thing is, if your system is sparse controllable, meaning if you can control your system using sparse inputs, definitely your system is going to be controllable. Because if you cannot control the system using any inputs, then you cannot hope to control it using sparse inputs. So sparse controllability immediately implies controllability. And we know controllability immediately implies PBH type test or Kalman type test. So if the system is sparse controllable, then the PBH test should succeed. The PBH test for the unconstrained system should succeed. That's one basic observation. Second observation is about the condition that we just derived. We saw that if the system is sparse controllable, then the Kalman rank type test that we derived in the previous slide should succeed, which immediately implies that there exists a finite K and a sequence of supports S1, S2, all the way to S capital K, such that the rank of the resulting controllability matrix should be equal to N. Now let's carefully look at the controllability matrix here. The first few columns of this controllability matrix are pre-multiplied by A. So you can see that in A is sitting, all the columns are such that they are pre-multiplied by A. So you can take that A outside, and then you can see that the first few columns, the span of the first few columns is nothing but it's actually the subset of span of A. Because you're multiplying A with something else, then you cannot increase the span. You'll also reduce your spanning set. So we can replace this first few columns of the controllability matrix with A. By doing that, you only increase a rank. You will never decrease the rank of A. But this particular matrix can have at most rank N. So we can say that if the Kalman rank type test succeeds, then rank of the matrix obtained by horizontally concatenating A and BSK should be equal to N. That's a very simple observation. Now, BSK has at most S columns because SK is your support set, and we restrict our support set to have at most S entries. So the number of columns of BSK is S, and that's the maximum rank of BSK. So this observation immediately implies that rank of A plus S should be greater than or equal to N. So let's recapitulate why we arrived here. So we said that sparse controllability implies Kalman rank type test succeeds, and that implied that rank of A plus X should be greater than or equal to N. So this is a necessary condition for sparse controllability to hold. So we got two necessary conditions. The first one is the PBH type test for unconstrained system should succeed, and the second one is a constraint on the sparsity. So these two are necessary for sparse controllability to hold. Interestingly, it can be shown that these two conditions are sufficient. So a system is said to be sparse controllable if these two conditions are satisfied. So with that, we can have the first result. So sparse controllability without any restriction from the support, if you allow to pick any S actuators at every time instant, then the controllability of the linear dynamical system changes as follows. We need two conditions to be satisfied. The first condition is the controllability of the unconstrained system, the controllability of the system without any constraints on the control input. And the second one is a lower bound on the sparsity. So sparsity should be greater than or equal to the nullity of the transition matrix A. So S should be greater than or equal to N minus rank of A. This is very intuitive because S is actually telling us how much are we restricting our control input. So if S is large, meaning we are allowing more and more actuators to control the system, and the system is more relaxed. And when S is equal to N, we allow a system to control all the actuators, which is equivalent to the unconstrained case. So when S is equal to N, second condition is automatically satisfied, and we will go back to the classical KBH test. And this condition tells us that we need a minimum value of S, below which the system is not sparse controllable. So this result is, this test not only gives us a very simple and polynomial time test to check sparse controllability, but it also gives us some insights to what is the minimum level of sparsity that we would need to control a system. So that minimum level is nothing but S should be greater than or equal to the nullity of the transition matrix. In control theory, we have something called Kalman decomposition. So what it does is, it in the conventional setting, Kalman decomposition will separate the state of the system into two parts. One part which is controllable and another part which is uncontrollable. And using this result, we can have something similar. We can have three parts or three parts of the system space. The first part is the sparse controllable part, that is the part of the state which is controllable using sparse inputs. The second part is sparse uncontrollable. That means that is controllable but not using sparse inputs. And the final part is uncontrollable. That part is not controllable using any inputs. So this result automatically gives us Kalman decomposition for decomposing your system state into three parts. I will not go into the details of how we do it, but you can check my papers, which I'll show at the end, to see how this is done. Another interesting result is about
one question. Can I ask a quick question?
Yes,
sure. So why is the sparsity level related to the rank of A? Do you have any intuition on that part?
So that is very clear from this explanation, right? So after the first, so basically when you try to control your system, your A matrix is multiplying all your columns. So if something is missing from the row space of A, you can only compensate using this B, right? This only term which is independent of A, right? And if the subspace of this whole thing, so basically B should compensate for what is missing from this subspace, right? So the nullity of this should be compensated by the columns of BSK. And in order to do that, one basic condition is that the number of columns in B should be greater or equal to nullity, or the dimension of the null space of B. So that is why you have a constraint on that.
Okay.
To make it more clearer, if you go back to the state space equations, yeah. So you can see, right? So your xk minus 1 is always getting multiplied with A. So if your xk sits in a space which is in the null space of A, you cannot achieve that using this guy. So you have to do something here. So that immediately implies that B times UK should span the null space of A in order to have to achieve anything here, right? So that immediately implies that your BS should span the null space of A. For that, you need at least S columns in B, where the S should be greater or equal to nullity of B.
Okay, thanks.
Okay, so the next result is on the number of sparse control inputs. So if you look at the Kalman type rank test, it ensures that you need at most n number of inputs to control a system. So the Kalman rank test, if you recall, we substituted capital K equal to n. So it tells that you need at most n inputs to control a system. So how does that change with sparse control inputs? So we have a bound on the number of input vectors. I will not go into the details, but the bottom line is the minimum number we need at most again n number of inputs to control the system. So the number of input vectors k star is upper bounded by capital N. In other words, we are not losing, in the worst case scenario, we are not losing anything by using a sparse control in the system. So the K is always upper bounded by N. We'll use this as slightly later when we discuss the design of control inputs. But with this, we'll conclude this part. This is a summary of what we discussed so far. We started with sparse controllability with fixed support. And we said when it's a fixed support case, we just start, we should check the PPH test for the system, which reduced system, where we replace B with BS, where S is a support of the control input, the fixed support of the control input. So we have to test the PPH test for A minus lambda times I times BS for all values of lambda, and for some, this should hold for some S, where the cardinality of S is at most S. Then we talked about sparse controllability without any restriction from the support. We said at any time instance, we can pick any S actuators. And in this case, the controllability condition reduces to controllability without any constraints. That is the classical controllability, and a lower bound, a lower bound on sparsity. So sparsity should be greater than or equal to nullity of A to ensure this thing happening. There are several extensions of this work. So the one extension is non-negative sparse controllability. So in addition to sparsity-constrained, suppose you have non-negativity constraints on your control input. That is, you cannot only influence your dynamical system in unidirectional way. You can only have positive control inputs. All the entries should be non-negative. So in this case, we can show that non-negative controllability and the same bound on sparsity will ensure you non-negative sparse controllability. The proof is quite involved, but the bottom line is non-negative controllability plus the same bound on sparsity will lead to non-negative sparse controllability. Another aspect that we can explore is output sparse controllability. So again, output sparse controllability has similar form as we discussed. So system is output sparse controllable if and only if it's output controllable, which is a necessary condition. And we also have some bounds on sparsity. So these bounds are not as simple as the bounds that we discussed so far. It's a bit involved. It also depends on your output matrix C. But there are the bounds on sparsity, which will ensure that output controllability plus these bounds will ensure output sparse controllability. Finally, we have the notion of stabilizability in control theory. So stabilizability is a weaker notion compared to controllability. What stabilizability says is that the vector, the system state xk should approach zero as k goes to infinity. So it's a limiting case. So it's a slightly weaker notion than controllability. But what is a surprising result here is that stabilizability without any constraints on the input will lead to sparse stabilizability. So unlike the controllability result, in this case, we don't have any constraints on sparsity S. Any stabilizable system is also sparse stabilizable. So these are different extensions of controllability notion that we have derived so far. Next, we quickly look at one simple case study, which deals with manipulation of social networks. So social network is a network connecting people. It could be a large network like Facebook or Twitter, or it could be a small network like people living in an area or people working in a company, etc. So what is a social opinion? Social opinion is the opinion of each individual about something. It could be a movie rating, it could be your opinion about a product, or it could be your opinion, your political view, etc. So who is trying to influence these kind of opinion? So there could be external manipulators like marketing agent or targeted fake news campaigns or political advertising, etc. So what is the goal of the manipulator here? The manipulator tries to control and change the public opinion in their favor. So they want to drive the public opinion or the network opinion is the system state here, and they want to change his opinion to their favor. And how do they do that? So they can do it under sparsity constraint. So at every time instant, they can influence a small number of people, because if it's large network of people, it may not be feasible to influence each and everybody. So what we do is we influence a small number of people who can in turn influence their neighbors, and in effect, at the end of the day, we can influence the entire network. So the budget or physical constraints can be directly translated to sparsity constraints, and we'll see how to manipulate a social network under sparsity constraint. So let's look at some examples. Let's say you are a marketing agent, so you can give some free samples to people. You can ask somebody to try out your product and see if it's good. And you cannot give free samples to everybody in the network. That is not feasible. So what you try to do is you try to give free samples to a few people and let them try it out, and then they can influence others. Another thing is an election campaign. So an election candidate can go visit some of his or her voters and talk to them, understand their problems, and probably pretend like they'll solve everything, and directly influence few people, few trusted voters, and let these voters influence others. So the question here is, and again, the election candidate cannot go to all the voters. Probably they can go to a couple of them. So again, you can only influence a few people in the network, which directly leads to sparsity constraint. Similarly, when a company offers a few free samples, then again, we have sparsity constraint, because these two are the cases where we influence only few people in the network. So the question here is it possible to manipulate the entire network opinion under such budget constraints? So you're only allowed to influence few people in the network, but yet you want to control the opinion of all the people in the entire social network. So that's what we're trying to see. So for that, we want to model the social network. So let's say we have n people in the social network. We can model them using a graph. So the nodes in the graph will represent different people, and the edges will represent their connections. So if two people talk to each other, if they influence each other, then we can link them using an edge. And if two people are unconnected, they don't know each other, then we don't have an edge. And so based on this graph, we can construct an adjacency matrix, which is a 0-1 matrix. So if two people are connected, we'll assign a 1, and if two people are unconnected, we'll assign a 0 in the adjacency matrix. Then we can construct something called a transition matrix in this case. The transition matrix will tell us how these people influence each other. So for the adjacency matrix, so for the weighted adjacency matrix, we take the Hadamard product of the original adjacency matrix, the 0-1 matrix, with a weight vector. So we construct something called WW transpose, where W denotes the weight of an individual's opinion in the network. So if somebody is a very trusted person in the network, he'll get a higher weight. And if somebody is not so trusted, then he'll get a lower weight. So we'll just rank the people in the network and assign them some weights. And that's what is denoted by W. There are n people, so everybody will get some weight based on their trust level in the network. And that will give you the vector W. And it can be shown that the adjacency matrix Hadamard product with WW transpose will tell you how these people would influence his or her neighbors. And finally, we have a lambda in the A bar. Lambda is a normalization factor. So that will ensure that the opinion of one person, the influence from the neighbors, is a convex combination of all the neighbors. So a person is influenced by his or her neighbors, then that influence is a convex combination of all the neighbors. So that gives us the A bar, which is the weighted adjacency matrix of this graph. How does the adjacency matrix look like? We can construct two types of graphs. One is the undirected graph, another one is a directed graph. Undirected graphs are like Facebook. Facebook friends are mutual. So in that case, the adjacency matrix is a symmetric matrix, because if node I is connected to node J, then node J is also connected to node I. So we get a symmetric matrix. And in this model, which we call the Edwards-Rennie random graph model, we pick the entries of the lower triangular part of the adjacency matrix from a Bernoulli distribution. So we pick it IAD Bernoulli distribution, and the upper half is the same as the lower half. So Aij is equal to Aji, because it's a symmetric matrix. We can also construct undirected graphs. like Twitter. So in that case, we can pick all the entries of the adjacency matrix randomly from a Bernoulli distribution. The parameter P of the Bernoulli distribution, the mean of the Bernoulli distribution, will tell us how densely the network is connected. For instance, if P equal to 0, then A is equal to 0 because your Bernoulli will always sample zeros from the Bernoulli distribution. So P equal to 0 is an extreme case where nobody is connected to anyone. And P equal to 1 is the other extreme, but everybody is connected to everyone else. So the P will determine like how dense are the connections in the network, or how dense are the edges in the network. So we look at an opinion dynamics model, which we call as a degree dynamics model, which is quite popular. What it says is that the opinion of a person in the network can be denoted by xk. So there are n people in the network, and therefore xk is an n-dimensional vector. So the ith entry of xk is the opinion of a person I at time k. For example, it could be your rating for a movie, or it could be whether you like a political party or not, or how much, what rating do you give to a political party or a particular product, etc. So xk could be some number. Every entry of xk could be some number. And xk is so everybody will have some opinion. So xk is an n-dimensional vector where each entry denotes the opinion of one person in the network. And xk evolves with time. So how does xk evolve? It has two components. One is the influence from the neighbors. That is what we denote by a bar times xk minus 1. So xk minus 1 is the network opinion at time k minus 1. And depending upon how your graph is connected and what is the trust level of your neighbors, you have some influence from your neighbors, which is denoted by a bar times xk minus 1. Plus, you have something called external control input, which is what your manipulators are doing. So if you're trying to influence somebody by giving a free sample, and that's what UK represents. So UK is the external influence from the manipulators, and a bar times xk minus 1 is the influence from your neighbors. And putting this together, we'll get the network opinion of an individual at time k. Then we also have a constraint on the manipulator. Manipulator can influence at most S individuals in the network at a time. So UK is at most S sparse. So the N0 norm of UK, or the number of non-zero entries in UK, is less than or equal to S. And this holds for all values of K. Now the question is, when is this system controllable? Or when is such a social network opinion system is vulnerable to a manipulator? So let's compare this model with what we have seen so far. So in our model, we had an input matrix B, but here we don't consider that. So the input matrix B is nothing but the identity matrix. And if you apply the classical PBH test here, B equal to identity matrix. In other words, we are always concatenating an identity matrix with something else. Then the rank of the whole matrix is always n, because there's an identity matrix that is always full rank. So rank of the matrix which comes from the PBH test is always full row rank. So the system is always controllable. So if you don't put any restriction on the manipulator, this particular system or this particular network opinion is always controllable. But what happens in the sparse case? In the sparse case, whether the system is controllable or not depends on the transition matrix, which is A bar in this case. So the sparse case depends on A bar. And we recall that A bar is a random matrix because A is random and the entries of A comes from Bernoulli distribution. So whether the system is controllable or not depends on the rank of A, which is a random matrix. So definitely we have some probabilistic results. So this is the kind of result that we have. We consider the evolution model with A bar, and so this is a result for undirected graphs. So it's a symmetric graph where the entries come from Bernoulli distribution with mean P. So it works under a small assumption. We want our P not to be too small or too large. So if P is between n minus s to the power 1 over n minus s and 1 minus 1 over n minus s, then the result holds. In other words, if your system is sparser, then we have a wider range for P. So if s is small, n minus s is large, then 1 over n minus s is small. So your P is the range of P is large. And we have a probability with which the network opinion is controllable. In other words, if we have a network of size n and edge probability p, and you restrict your control inputs to be sparse, and we assume that at most s entries of the control input can be non-zero, then the network opinion is controllable with the probability given in this box. So we look at what it means. So first of all, we know that as sparsity S increases, so when S increases, the system, the inputs become more and more dense, which means the system is more relaxed. Then we can see that the number of terms in the summation also increases because the summation goes from I equal to 0 to S. So as sparsity increases, there are more terms in the summation, which naturally implies that the system is more controllable, which is intuitive. Now what happens as the network size increases? So if n goes to infinity, you can see that we have a term like e power something in terms of n. So as n goes to infinity, that e power term goes to 0, and the bound is greater than or equal to 1. But we know that the probability is always bounded by 1. So as n goes to infinity, the bound also goes to 1. So in other words, if the network size is very large as n goes to infinity, the system is always controllable, no matter what is your sparsity or what is your p. So as long as sparsity S is greater than 0, this holds. We recall that we had some bounds on p. So we said that when p is too small and p is too large, it doesn't work. So let's see what happens to the bound as p goes to 0. So if you analyze the system, and if as p goes to 0, the bound actually goes to 0. So that is kind of intuitive, because when p goes to 0, we said edge probability is 0. So there is no edge in the graph. The people don't talk to each other. A is equal to 0. So people cannot influence each other. Then the system is not controllable. And we said the result will not hold for that regime. But if you look at the bound, we can see that the bound also goes to 0 as p goes to 0. So our result holds in when p is small. But on the other hand, when p is equal to 1 or p goes to 1, everybody is connected to everyone else. So A will have all entries of A will be 1. And in that case, if we calculate the controllability probability, that goes to 1, but our bound doesn't go to 1. So in other words, although we have restriction on p, our result holds for small values of p, but it doesn't hold for large values of p. I'll show you some example simulation result. So this is a graph which shows the controllability probability versus the network size. So here you can see that as the network size increases, the probability of controllability also increases. This is not the bound that I derived. This is the actual probability of controllability that we manually calculated. So as n increases, so in this case, as n is greater than 25 or 30, your system is controllable. So large networks are always vulnerable to sparse manipulators. And if you plot the probability of controllability versus the edge probability p, we can see that when p equal to 0, the actual probability of controllability is 0. So is the bound. And as you increase your probability, your bound increases. It comes down and then goes up. So our bound doesn't really capture this part, the last part where the bound actually goes down and then comes back. So as p goes to 1, the bound doesn't hold. But when p goes to 1, the probability of controllability is actually going to 1. To summarize our results, so we talked about controllability using sparse inputs. We derived the polynomial time verification test. And sparse controllability is ensured by applying at most n inputs. Then we talked about opinion dynamics, and we said if we don't put any restrictions on the manipulator, the system is controllable with probability 1. But if you put some constraints on the manipulator, if you put sparsity constraints, then the probability of manipulator success will naturally increase with network size and sparsity. And if you make the network size large, the opinion on the asymptotically large network is always controllable. It's controllable almost surely. So this is what we have seen so far. Now I'll quickly walk you through the design of sparse control inputs. This is going to take a minute or two. We won't go into the details. So the sparse control design problem is about finding what are the correct U1s, U2, and all the way to UKs, which can solve your system of equations. So we said controllability will ensure that the system has a solution. But what is that solution is a more challenging question. So given an initial state and a final state, how do we choose, or how do you design the sparse inputs which can drive your system from the initial state to your final state? So that is what we're going to look at. We recall that we have already shown that we need at most n sparse inputs to drive your system from any initial state to any final state. So clearly we need to solve for n sparse inputs. So in that case, we can substitute for a capital K as n. So if capital K is equal to n, you have x final minus a power capital N times x in it is equal to your controllability matrix, again with K substituted with n, times U1, U2 all the way up to Un. So you have n control inputs. So if you put K equal to n, on the right hand side, in the left hand side, you have an n dimensional vector, which is a known vector, because x final, x in it, and a, n, everything is known to us. And right hand side, we get a matrix, which is the controllability matrix. Let's call it as phi. So you have x tilde equal to phi times u, where u is again obtained by concatenating all these sparse inputs. So the question is, how do you solve for such a u? Given x tilde and phi, how do you solve for u? So one simple approach is to use the standard compress sensing or sparse recovery algorithms. You can use something like Lasso or OMP or thermal matching pursuit or Sparse machine learning or any of your favorite compress sensing algorithm, and to try to solve for u from x tilde and phi. But the problem is the standard compress sensing algorithms will give you a sparse vector, but it does not ensure the sparsity of individual blocks. So the UKs may not be sparse. Whatever you obtain by your compress sensing algorithms do not ensure the sparsity constraint on each of the input vectors. So what do we do? So for that, we need to look at the structure more carefully. So in this picture, I have shown two examples. So these are two vectors of size 250, and we just plot the values corresponding to each of them. So if you look at the plot on the top, it's a general sparse signal. So what I mean is, it is a sparse signal. It has a lot of zeros. You can see that a lot of bubbles are around zeros, and it has a few non-zero coefficients. But these the non-zero entries could be anywhere. So you don't have any pattern for the general sparse signal. But if you look at this, the next picture, the one at the bottom, that's a piecewise sparse signal. So how is that different? So here, each piece, so you can, which are denoted by these lines there. So each piece is sparse. So here you can see that every piece is two sparse. So the sparse and non-zero entries are spread across all the 250 entries. It's not, so for the first case, you have a bunch of zeros followed by a bunch of non-zeros. It's all mixed up. But if you have a piecewise sparse signal, it's a large signal formed by concatenating different sparse signals. So if you look at each piece at the sparse, but that may not be the case for a general sparse signal. So this is a special structure, and we call it as piecewise sparsity, meaning every piece is sparse. So we need specialized algorithms to solve these, and there are a few algorithms in the literature that solve this problem. The one was called piecewise OMP or piecewise orthogonal matching pursuit, but there aren't many algorithms that solve this kind of sparse structure. Suppose you look at the case where it is time invariant. If it's the support is time invariant, then your U1, U2 all the way up to UN will have the same support. So we can rearrange this big long vector U in this case to get something called a block sparse vector. So for example, look at the picture that I've shown here. The first block is your U1, the second block is your U2, and the third block is your U3. Let's assume the case where you have capital N equal to 3. So everybody will have the same support. So if you look at the non-zero entries denoted by the colored boxes here, the non-zero entries are the same here. But I've shown everything with blue color, but the non-zero entry, the first non-zero entry corresponding to the first vector will not be the same as that of the second. So what we can do is we can rearrange this a bit. So what we do is we take the first entries of all the blocks, stack them together. We take the second entries of all the blocks, stack them together, and so on and so forth. Since all the blocks have the same support pattern, if we rearrange it this way, what we get is for the indices which are non-zero, we get a block of non-zero entries. And if an index is 0, then we get a block of zeros. So here n is equal to 3, and then let's say each block is of size L. And after rearranging this, you get L blocks. And if an index belongs to the true support, then the corresponding block in the concatenated vector or the rearranged vector will be all non-zeros. And if the index is missing from the support, you'll be all zeros. So we have a bunch of zeros and bunch of non-zeros sitting together. So to illustrate it better, if you look at it along with the previous picture that we saw, for a general sparse vector, we can have non-zero entries spread out at different locations. And if you have block sparse vector, for every block is either full zeros or it's dense. So it's so every block, if you look at every block, it's either all zeros or it's all non-zeros. And what happens in a piecewise case? In a piecewise case, you have, if you look at every block or every piece is sparse. So piecewise sparsity and block sparsity are kind of opposites to each other. Piecewise sparse vectors will arise in a case where the support is time varying, and block sparse signal will arise in a case where the support is time invariant or the support is fixed. So these are some of the algorithms available in the literature to solve such systems. So piecewise sparsity, we have few algorithms like piecewise OMP, piecewise inverse scale space algorithm, etc. But on the other hand, block sparsity is a very well studied topic. So there are plenty of algorithms in compression literature like block OMP, group lasso, block SPL, learn block SPL, etc., which can solve this particular problem. To summarize, we work with the state space model, and we consider sparsity constraint. That is, our inputs are more restricted than the conventional case where we don't have any restrictions on inputs. And we said in the non-sparse case, we typically use least square base solution to find the control input. But when we have sparsity constraints, we have to either use some block sparse algorithms or we have to use piecewise sparse recovery algorithms to solve them. So we have a couple of algorithms in the literature which can do it for us. And regarding the feasibility of such inputs, in the non-sparse case or in the conventional case, we have a Kalman rank test or PBH test, and it says that the number of inputs should be equal to n. But in the sparse case, we have PBH test plus a bound on the sparsity. And we again saw that in the worst case, the number of inputs that we would need is k equal to capital N. We also looked at the opinion dynamics as a case study. Open problems. So this is a very, I think, very recent topic, or it's an upcoming topic. I would say it's not very matured yet. So one simple question is sparsity enough? Because we also want to handle something like energy constraints along with sparsity constraint. Another question is, we consider two cases. One is the support is fixed, another is support is time varying. But these are the two extreme cases. So can we do something in between? So can we consider a case where the support is changing, but the changes are not drastic? So what if we have slowly varying support, or can we involve something like a switching cost if you want to change the support, etc. And also, I said piecewise sparsity is an underexplored area. So can we come up with new algorithms to do that? Maybe deep learning based algorithms to develop piecewise sparse recovery algorithms. And also, what are the other notions of controllability? For example, if you have a stochastic system, can we have newer notion of controllability? And more importantly, can we have newer applications that are related to networks, or can we connect it to batch signal processing, or etc. to have to find new applications of this particular area. So these are some of the papers that I have covered with different people, different research groups. There are many papers which are under review process. So I have worked with a lot of people from IISc. So I worked with Chandra and two of his master's students, Chandrasekhar and Rupam. At Syracuse University, I worked with Professor Pramod Kumar Vashni, and at Cornell University, I worked with Vikram and his student Budika. So with that, I conclude my talk. I'll take any questions if there are.
Yeah,
Thank
I
you,
have
Dr.
one
Joseph.
question.
Yes.
Yeah, go ahead.
So in the time varying case, do you have any insights on how does the support change over time? Like it will depend on the matrices A and B, right? So I'm
Yes.
assuming that in the time varying case, since you are allowed to change your support over time, you can influence different states at different time instants, right? So I would assume that there should be some pattern or something there. So,
Yeah. So there are two ways to look at it. So one option is you can just so one thing is we don't know if there is one sequence of support will work for everything. So one thing is you can just try to solve this equation directly using not this equation, but this one using any of your P-Spice sparse recovery algorithm to check if there exists what is the support that will work. Another option is to look at the system of equations, and as we said earlier. Yeah, so this is the kind of system that we need to work with, right? So let's say you want to find S1, S2 all the way to Sk such that this equation is satisfied, and this S1, S2, up to Sk will tell you what support will work. So clearly, if you want to pick Sk, we need to pick the columns of B such that it spans the nullity of A, right? Because all these columns belong to the span of A. And if you want to rank to be n, then the columns we want to pick Sk such that the columns of B will span the nullity of A. So applying the same logic, we can look at these set of columns. So if you ignore this particular one, all of these are subset of span of A squared. So we want to pick these guys, that is Sk minus 1, such that it will span the nullity of A square minus nullity of A, or the null space of A square minus null space of A, and so on and so forth. So that could be an intuitive explanation on how to choose the support.
okay.
So if you look at, I have a paper on output controllability. So if you look at that paper, it clearly tells you how to construct how to find the supports which will satisfy this particular equation.
Right. And one last question. So you also mentioned about stabilizability problem without any bounds on sparsity. So just curious, like if it does not depend on sparsity, then you can have a zero control input.
No, so these results will apply only if S is greater than 0. That is a requirement.
Okay, so you're saying that S equal to 1 will work in that case?
Yes, S equal to 1 will work.
It has to be larger than or equal to 1.
Yes.
Okay, thanks.
Any other question? If there are no more questions, let's end this session. Let's thank Dr. Joseph for an interesting talk. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will also be posted on the webpage. Thank you and have a great evening.
Yeah, thank you.